session. So, by considering the time, I'm shortly introducing here him. Hello,
Hello. Yeah.
welcome, sir.
Yes. Yes. Can I
So,
share the screen?
sir,
Yeah. Shall I share the screen and
yes, sir, you will share. Sir.
okay. So, are you able to see the screen? Is the screen visible to you?
Yes, sir, it's visible, sir.
Okay. So, shall I start? Shall we continue? Hello. Okay. So, I'm starting now. Is voice audible for you or it's low?
Yes, sir. It is audible, sir. You
Audible,
can
right?
start, please. Yes, sir.
Okay. Yes. Just I'm confirming. So today I was talking too much, little more technical, which is like the solidification side of the advanced material manufacturing. This is a different technology, something called directional solidification technology, and this will be the topic for the today's presentation. And to give brief introduction about me, my name is Shanmukha Kiran Aramanda, and right now I am doing postdoctoral research at University of Michigan, USA, and I did my masters from IT Madras and PhD from ISC Bangalore. So I will be showing different things, and one main thing between you and me is that I'm mainly a metallurgy and materials engineering guy from the background of metallurgy, and you are all mostly, maybe I expect to be like mechanical, so try to be a little bit slightly different, so we'll try to catch up with that. Let's see, slide is just 1 minute. Just give me a minute. These slides are trying to take time. Mm, Just again resharing. Oh, it's not showing on screen. So are you now able to see?
Yes, sir.
Okay. Okay. So in this talk, I will be mostly focusing on solidification and phase transformation, which is like some structure and phenomena that happens in the materials, inside the materials, which involves the fundamental understanding of how the structure, which is in the micron level inside the material, is like evolving with time, and how that is useful for applications, and how that will help to generate advanced materials. I guess all of you know what is meant by solidification, which is nothing but the liquid to solid transformation, and how that transformation affect some structure inside the material, and that material structure, how will it affect the property. So to understand that, there are two aspects to it. This how we manufacture the material, that is something like advanced manufacturing, which has like a controlled experiments beyond regular experiments. For that, we may need to do uh, design apparatus and methods and experiments. The second aspect is to see how microstructure or the structure inside the material with our characterization techniques. This can be like in 3D, we can see the microstructure, or we can also see through in situ experiment. In situ experiment means you can see when solid is forming from the liquid, or it's when some phenomena or some process is happening, capturing with camera how that process is happening. That is called in situ experiments. We can capture that and see how really some solid material structures are forming. Also, something called multimodal imaging, which is called you can use different techniques and then understand how the material inside structures are there. Similarly, in 3D, some image processing and other things to quantify or to understand much better about the material. So these are two important things that are required to make a good advanced material. So by combining this is outline of the presentation, which contains advanced manufacturing, solidification, and characterization. So this will be covered in this talk. So what do I mean by advanced manufacturing? So what I think here is that how well we control the process, whatever the process is happening during the manufacture. If we have more control on the processing condition, then it is a controlled experiment, and such controlled experiments leads to very advanced manufacturing. Then it leads to advanced material production. So for as we are discussing during the solidification process, the main parameters during solidification, the process parameters are like how you are cooling the liquid, what is the thermal gradient. Thermal gradient means how temperature is changing with the distance, and velocity. This is like how fast you are propagating the solid liquid interface, and how is the orientation of crystal. So the material has some crystal structure. If you know FCC, BCC, that crystal have different orientation of 111, 100, different planes. How that orientation will also affect the property. So these are some of the parameters that are important for the production or the manufacturing of advanced materials. So then what is the actual challenge in doing this controlled processes? If I'm just showing one schematic with a liquid, assuming this is a liquid and this is solid, when you are cooling this, so the liquid, it's transforming into solid, and if you are cooling from one side to other side, the solid is propagating like this. So when this is propagating like this, there is a problem. The thing is, if you want to mathematically solve how this is evolving, you have to balance the energy at the flux of the heat at the boundary. Then it is nothing but the heat flux in the solid and the heat flux in the liquid. If we have balance, that leads to how much heat is generated at the solid liquid interface. So this should be, people call this as Stefan condition, where this is the amount of heat released at the solid liquid interface, and this is the heat flux in the solid, and this is a heat flux in the liquid. But the flux equation already have a thermal gradient here thermal gradient. This is how temperature is changing with distance, and this is the velocity. So if you have an equation with these two parameters in same equation, that means both are actually coupled to each other. So if they are coupled each other, you cannot change this without changing this. So we can do better, as per the last slide, we can do better advanced processes only if we can control this and this independent of each other. So how well we can do that is the important question. In normal casting, if you want to do, you cannot control both of them separately. Both are dependent on each other. When you are cooling, you have continuous release of latent heat with a velocity, and also we have different thermal gradient. So doing solidification with normal casting is easy, but we want precise control. How we can do the precise control? But before we go into precise control, what is the advantage of the structures that we can get with good control leads to how well we get good structures. For that, I want to show some of the images that are taken from the microscope of a material inside a material by different velocity or different cooling conditions. Or if we are doing slow liquid to solid transformation or fast, how will it affect the transformation? So this, don't forget, don't confuse with this. I will skip that. For example, I'm taking a material which is tin, and I have added something up to some 4% of zinc. This is this composition. This is something called phase diagram, where it melts is given by this phase diagram, and how with each composition of zinc, how when the alloy melts is given by this phase diagram. So pure tin melts at 232, whereas 4% zinc will melt at this line, along this line. So yeah, if you don't know this, that is fine. But what I want to say is this alloy is taken with 4% of zinc in the tin alloy, and it is cooled at a very slow rate, like zero point 0.5 micrometer per second, and little faster 2 micrometer per second, and very fast 25 micrometer per second, with one gradient like 21 Celsius per millimeter. So the first case, when we see in the microscope, we see single full block like this, which I just showing like a schematic, like from the liquid, the single phase is coming this way. But it is when it is cooled with very high speed, the microstructure, when we see in the microscope, it shows something like this yellow thing, which is cut in the cross section. That's why it looks like this. These are all the cross section images where you can see so many circular features here. And by increasing furthermore, we can see something like dendrite type structure with completely periodic structure. So what it implies is the same alloy, same material. If you do a different process condition, the interior of the material is changed. That means by changing how you are cooling, you can change your material. That will change the property. That will change the entire the material application. So that is where how you cool is more important, and how you get internal structure is very important. This is one example. Similarly, so here, that is what the point, that thermal gradient and velocity are important. From this planar type, this is called planar, this is like cellular, and this is like dendritic. For this transformation, these conditions are very important. So there is something other thing called eutectic solidification. In the this eutectic solidification means from one liquid, two two type of materials will form inside the solid. When we see in microscope, we can see tin. Also, we can see zinc. There are two elements. They are separately formed inside the material when we see only in the microscope. So that is possible with this red line of composition, like around 10 percentage of zinc and 90% of tin if we take. And if we cool it slowly, we can get one type of structure. So this all white color is the tin, the black things are the zinc. So this is also when we see in the microscope, we can see two type of feature, one tin, one zinc, with a very random arrangement of zinc. So again, here also, when we maybe do very controlled experiment with a very slow 0.6 micron per second to 50 micron per second, what we can see, See, this white thing is tin, black thing is zinc. So we can see how well they are organized. They are like periodically they are like formed. So we can get some structure like that with very controlled experiment. And when we go further and further increasing the velocity, we can see very fine zinc with all this is same fraction. Only difference is here the big one is split into very small pieces here inside the material. So when we do any mechanical test or when we do any different type of test, this material behavior and this material behavior is different. So the same alloy, we can create different internal structure, and that can be that can be made into a good advanced material. So this is again too much technical. So what I want to say is the velocity of the cooling condition during solidification is important for formation of the length size and the morphology. Like this is like a line and this is like a dot. So this morphology and the length, that all dependent on this velocity inside a material. So again, the making of material is very important from this observation. So this is another type of cooling. So in this is actually when we do as cast, like just pour the this composition of silver zinc in a mold. You see some of the structure like this. But if we do with the control experiment, the structures you see will be completely different. So for that, I will show two different condition. These are two different condition. In two condition, how that microstructure or the structure inside material, this white thing I will be showing like red color, and the black thing I will show like blue color. So you see here, this is the material. In this material, this become like a two band type structure. So here I am showing in the 3D. So don't get confused with the 2D image. This 3D image is obtained by doing something called CT scan, which we generally do for our body and so on, something like that. So here you can see a different type of structure. You can see here a different type of structure. So the overall point is that again in another type of material also we can get a different type of structure with different cooling condition. So here, this if we see G by V and here G by V, they are almost similar, but we see different structure. That means it is not only G means the thermal gradient, V is the velocity. So gradient by velocity is not only the important factor. Each value of G and V are also important. So what I want to say is that this condition is also should be controlled so that we can get better microstructure, which maybe improves better than what I am showing also. Similarly, in another case, you can see in this type of material, you see at one condition there is a random distribution of particles inside the material. Here there are like very organized, well organized, like layer type materials. The distribution. This is also just happened because of cooling properly from the liquid. When liquid is cooled with a particular condition, that leads to these two different type of structures, which made just with the cooling condition. So here is where the gradient is important, because these two are done at same velocity, but they are done with different gradient. The gradient is how temperature is changing when you are cooling. So that is also important, just to show that that's where this is important. Finally, one more other place where if you want to add particles into the material, in a liquid you are putting particle and you want to keep it inside the material, it can have two options like this. When solid is growing into the liquid, when you are solidifying, the solid can push the particle, or the particle get engulfed, means it get trapped inside the material, or it can form this structure, So many possibilities are there. All by controlling the condition, you can get whatever you want, and that can lead to a good property of the material. So similarly, the solid liquid can be flat, I was showing. It can be like curved in this direction or in this direction. These all will lead to different type of properties, and different type of material is formed with different type of the interfaces when you are cooling from the liquid. That, suppose assuming this is a liquid, then this is cooled to this. So different ones leads to different resulting internal structures as well as the properties of the material. So the control of process condition is very important from this understanding. So with this, now how we can control the process condition is important. How we can control the process condition is what we are going to see now. As we are seeing, this is a condition where we are talking this velocity and this is coupled. So this can be made decoupled by doing something called directional solidification. This is the main discussion of the talk, where you can keep it. It will be, I will take time to explain what is happening here. So there will be two zones. This is like hot zone where you keep a crucible with full metal inside, and you have something called cold zone where material is like, here the condition is like cold, here it is hot. When you put your material inside a crucible and put it in this zone, all the solid will melt, and we set the temperature above the melting point of that material. Suppose if it is aluminum, we will set above the melting point of aluminum. Then every solid gets melted, and the metal become a liquid here in this stage, and you can bring this down slowly. When you bring this down slowly, you can see something like this. So initially this is completely liquid. After bringing it down, it solidify like this in the black color, and there is a something called solid liquid interface as shown here. So the rate at which you bring it down sets the velocity of the solid liquid interface, and the temperature difference between here and here, how much temperature you are maintaining gives the thermal gradient. So by controlling these two temperatures, we can control thermal gradient. The rate at which you pull down will control the velocity. So in this way, we can control thermal gradient and the velocity of the solidification. So this way of doing from top to bottom or doing in one direction is called the directional solidification. That is where you can control the thermal gradient and velocity that leads to the advanced microstructures and leads to advanced material development. So similarly, in the process of developing the material or the directional solidification operators, so if we have just a hot zone and chill zone or the cold zone, this cold zone is with a water circulating unit, and the hot zone is just with alumina and heating element. And if we measure the temperature from top to bottom, and from each location how the temperature is varying, if we record, it shows something like this. So at the top, if you set the heater temperature to 400, if you bring at each location and check the temperature in along this line, you see something like this. So the issue here is the gradient need to be better, and there is inside the hot zone there is a slope here. We don't want that to be slope, that we want to be straight, because if you have a change in temperature from 500 to 400 inside the hot zone, that leads to a thermal gradient in liquid, because we keep the sample in liquid state in the top zone. When we keep it in the liquid state, when there is a thermal gradient in liquid, that can cause also convection inside the liquid, and that convection will again change microstructure or the structure inside the material, and that leads to a different type of material than expected. To make this very homogeneous temperature, what we can do is we can put a copper rod here. Copper has very high conducting, thermal conducting, so that makes all the temperatures in this part are uniform. So for different set temperatures like 300 to 550, you can see almost a straight line at each of the condition for each set temperature of the hard zone with same fixed temperature of chill zone. We can see that there is a variation which is like that. So where this implies that this is almost like a straight line compared to the top one. So this will help in order to make the thermal gradient in the liquid low, but the gradient in the in between both zones to be high, and at the same time there is a liquid convection is reduced inside the top zone. Further, the copper get oxidized if we keep for longer time, so that leads to development of nickel plated copper rods. So we can deposit nickel on the copper, and that leads to a good property of the material. And this is one design of the furnace with copper plate or copper rod being placed inside that. So again, the another way to improve further of the directional solidification technology is that as we see this here, we are keeping sample like that with a wire or with a rod we can put, and we can keep the sample like that. And second way is to keep within a holder, you can insert the rod. And now in the second case, what we can do is we can also supply water to the black body, the black region that I am showing, which is a sample holder. That makes the what happens with that is it has extra heat absorbing or maintain constant temperature at the bottom. So this is something like what we design to keep sample inside this. This is from the top view. You can put a sample here, and water goes into this, and then it gets continuously cooled, and then water goes out. So this way we can design from one thing which has no water cooling or anything to with something called water cooling. With water cooling, the advantage is we can take out most heat from the sample, because there's a lot of heat is there, because from top zone the molten liquid is giving a lot of heat to the sample that can be extracted out through the supply of water. And this leads to more process variables, like you can increase to higher gradient, and increasing higher gradient leads to also we can also use the higher velocities. So we can increase more type of processing condition, which can lead to more variables in the process condition, leads to more process derived microstructures or the structure inside the material. So this is another way. So the other way is also to, instead of using this, we can use some liquid metal or even water directly, and all material will go into that. So then the heat equation consists of one more term. Forget about that. But what I want to say is you can put the entire crucible into a melt of liquid or some water. Then that is additional cooling that leads to much more different type of processing condition. So these are different process condition that makes to generate different microstructure that I was showing before. So to understand this, to quantify this, we did also some model. I will go through it very fast. These things also. So some benchmarks we did with different cooling rates, and as I was showing this before also, with velocity and with the spacing measured between the each of the tin and zinc phases here, what we notice is they are following a trend. That means the materials behave with something like spacing and velocity. They follow some person called Jackson Hunt. He named some spacing. So he, according to that, it follows some rule of that equation. So what it means is, if you control with a specific velocity, you can get a structure of or the spacing of the material, the microstructure inside, with whatever you want. Suppose if you increase this v, you will decrease the lambda. If you decrease v, you are increasing lambda. That is what you are also seeing here. So with that, you can design a microstructure whatever you want, with desired size and shape of the features inside the material. So that is actually like controlling the structure inside the material. So coming to the real operators DS technology that we have developed, this is my PhD thesis. So I made everything from the scratch. Like, we have taken the heating element and then winded it to a alumina tube, and then we put ceramic cement paste, and then this is wrapped up with a wool, and then connected to electric circuit, and or the heater controllers. And similarly, this is the water cooling body, and this is also added to the bottom, and all this assemble is put on this linear drive. You can move the sample from bottom to top, top to bottom, or you can move the furnace top to bottom or bottom to top. Here, these two setups are made such that you can move the furnace, not the sample. So sample will stand like this, and it will go into this furnace. This bottom part is cooler. This is that cooler, and inside the top one, which is the furnace, you can melt any alloy, and you slowly cool to the this part, while you are bringing a different rate that is used with this help of this drive. You can bring at very slow velocity, or you can bring at very high velocity, or you can do different velocity. And when you are bringing from the top to bottom, you can generate different internal structure of same material, and that has a different application. So these are two similar type of things. With this, we have a control on different velocities and different temperatures up to 1000, and this was like easy to maintain. And this is a high cooling with a water cooling body. So to compare the difference between this furnace with something like this is what I did from my PhD. And in the University of Michigan, they have some commercial setup they purchased from some other company, MTI. So there is a difference when we do same experiment in different places, because the process conditions are not same. Here water cooling is there, here no water cooling is there. That leads to different microstructures. For example, this is something called peritectic solidification. In that, we see one band and one of this structure, whereas in another case, so I want to compare it like in the peritectic system, what I showed previously. From this setup, this type of structure is obtained. From this type of structure is obtained. Here, random structures are there. Here, more periodic structures are there. The point is that if we make ourselves the equipment, we can make more. So these are actually good structure compared to the top ones. So we can make good structures if we make everything by ourselves. We can have good control of how we can do the process. So that leads to a good material, and that good material will have good application. So after that, I was during after my PhD is done, we had developed some other material. So here we are solidifying something called CMSX super alloy. This is a very high temperature alloy. This alloy is used as a turbine blade in aerospace applications, something like in aeroplane. Some very high temperature is exposed to some blades, when the fuel is running. So for that material, this alloy is generally used. So this alloy we try to solidify, and we try to get a nice microstructure. We can see some microstructure or the structure inside that. So we try to obtain better properties of that, and that is all possible just because this furnace all setup is also designed and developed by us. Similarly, some refractory elements are also made, and it leads to also this kind of microstructure, the structure that you see. So the takeaway is that we should make better furnaces, and then it leads to good material development. So some more other ways we are trying, or we tried, is making the growth of material like in a spiral. You can see spiral. So here the solidification, or the initially all the material filled inside, and that is melted and then started solidifying from one side to other side. Here it will go directional. Once it reaches this part, it will solidify like this. And even in this case same, but when we cut and see that material under microscope, you can see some of the structure also form like that spiral. It follows the structure also go like that. So the motivation is that if you want to make some different structure inside material, you can adopt this kind of technology and make some internal structure with different type of visualization. So that means same alloys or same material, you can generate into multiple ways, variants of same material. Internal structure is different. Similarly, in another case, we have done like bending the material when it is solidifying. So I'm not going so much into it, but here also we see some bending happening from the straight part. So that is something very interesting. Um, Similarly, I was showing some velocity of increase, some velocity or different velocity. Here we did some experiment like from one velocity to other velocity, 32 to 0.5. We have changed the, while it is growing, we change. So then what happened is the microstructure also is changing with the time. So you can see very fine features here. As it grows, it become like very coarse feature. Similarly, we did opposite. Here it is not gradual, it is like sharp change suddenly happening, and you can see very coarse structure to very fine structure. Again, both are same material, but it leads to different type of microstructure, sharp, continuous, everything. So what I'm trying to focus or telling again and again is the microstructure or the structure inside material can be tuned with the process we are employing. So how well we control the process will control how well we see the structure, and that is very important. Again and again I was saying the same point. So in one case, um, I will discuss, till now I was discussing about how we can control the process condition. Now I will explain one more topic of eutectic solidification, where one liquid forms into two solids, and how that structure can be useful in developing a new material. So in binary means only two elements are there. Eutectic solidification means when you are cooling the liquid, it forms two solid. In the previous case, I was showing tin and zinc. In some other cases, it can be silver, copper. In some other cases, some two different things. It is again, I can give analog like if you have salt and water, when you are mixed in the liquid state, both salt and water will dissolve in each other, and you have a single solution of salt water. But when you cool it to solid ice, do you think it will be forming as uh, ice and salt crystal, or it will be single phase of ice? So that is very interesting. In some cases, some salts, they form like ice gets split and salt gets split. Then it leads to the when they are in the liquid state, they are all same phase, but when they are cooled down, they become like two different solids. So similarly, in that type of material, if you are cooling a liquid, it forms into two solids. When you cool that material into two solids, and if we go and cut the material and see under microscope how that microstructure is changed, and with the knowledge of the directional solidification and processing condition, how we can get different internal structure, and how we can get the properties whatever we want. So when you are cooling from the liquid state, atoms can be like the top is like liquid atoms, the solid is the below. So the solid atoms are more compact, like they are like very closely packed. In the liquid state, they are very loosely packed. So when you are cooling liquid to solid, two type of solids can be possible. In one solid, the solid atoms are lying in one particular straight line. In another case, the solid can be zigzag. So this is called rough. This is called smooth. So in this kind of situation, one type of behavior of solid phase is there, but when you have different type of interface, this is solid liquid interface in the atomic. If we see in the atomic level, so these two leads to different type of structures. So now if you have, when you are cooling in the eutectic system, two solids I am talking. So if one is like this and one is like this, then it is a different material. If both are like this, if both are like this, then it leads to different structure. Now I will show how each case, how microstructure or the structure will be there. Now I will take two non-facet. Non-facet means it is rough. So if both solid, when you are cooling, is forming like rough, in that case, so this is alpha beta. This is liquid. When you are cooling the liquid, alpha beta alpha beta alpha beta are forming. So what happens is this organize. So this alpha send whatever atoms b want, beta want, and beta will send whatever alpha atoms want. They organize periodically based on the diffusion happening before they are growing. Suppose they are growing like this, so the diffusion happen, b atoms goes here and join in beta, and a atoms goes to alpha, and then they grow like that. When they grow like that, then it leads to something called in two type of structures. Either they form like lamellar type structure, where alpha beta are arranged in this fashion in the material, and it can also form like rod type of feature. They, so one phase having more fraction has this type of feature. The minor phase will be like rod. In this case, all both phases have similar fraction in the sense both are 50-50. Then it is like this. So also previously I was showing the velocity at which you are cooling will also change your spacing. So in that way you can have different structures, also different sizes of the structures. So that is all possible with the non-faceted type of systems. In the case of faceted system, as I was saying, this is like a sharp uh, type of solid liquid interface. This is liquid, so this forms like sharp, and they go like very random. So this is very regular, and because of this is very regular, lot of people in the metallurgy community, they study this type of material. This lamellar type is good for mechanical properties, so people try to get this type of microstructure inside the material which have good property. So this is very random, and this is not much useful. So because of that, this was very well studied, and this is not mainly our interest. But the interesting thing is here I'm talking both faceted, both non-faceted. But if one is faceted and other is non-faceted, like one is rough, one is smooth, when we see with different fraction of phases, see this structure in the aluminum alloy. When you add nickel, it leads to a different dotted type of microstructure. In aluminum silicon, this is the most used cast alloy in the foundries. They see a structure. This is full of aluminum. The black things what you are seeing is the silicon. So silicon forms something very interesting like this when you see under the microscope. Further, if you see in the tin bismuth type of system, so when you cool this liquid and see in the microscope, you see something like a threefold symmetry type of thing. Here, something close to fishbone type of structure, and other places alpha beta are arranged very randomly, unlike here and here. So this is another type of microstructure with silver and antimony type of material. You can see one phase, one material is Ag3Sb and other is Sb. They form very interesting type of structure with three fishbone type of things joined at the same location. This is another interesting example. When you see under microscope, you can see again threefold or three lines, and the eutectic or whatever the two phase I was saying, they are growing like a tilted in this case. So these are all something when we see under the microscope, different structures are there. I want to make sure that you understand there are things that are seen inside the material also under the microscope that I am trying to show. These are all will be helpful to understand the property of the material. In aluminum, germanium, we can see a different type of structure. This is actually in aluminum germanium. You can see this. This is maybe close to something of this type, but this is slightly different. In this is other interesting thing. Magnesium and zinc alloys, you see a material which is like a spiral. This microstructure is interesting, and this is also another interesting structure where it forms like a G type of material. So these are all different type of structures that are possible, and that can be obtained, and these are all possible with the directional solidification technology with different control of process condition like velocity and gradient for this type of alloys. So this type of material also, there is something in 3D how uh, these are coming to this type of shapes is actually in the 3D. Some mechanism is happening that is leading to this type of material, and this involve very complex type of these are very complex structures that are forming inside material. So to understand this, we need to see in real time solidification, or really when you are cooling a liquid. So also some people do phase field type simulations, people do, and some of that also are little bit difficult for how the structures are forming inside the material. So what finally is that these materials are how they are forming this type of structure is very important to understand, and for that we need to see real time when you're cooling with a camera capturing how this is happening. So I want to show that in the next slides. Hello.
Yes, sir. You're audible, sir.
Yes, screen.
Sir, you are audible, sir.
Okay, okay. So yeah, I am continuing. So what is in situ solidification and why it matters? So what we are capturing is real time dynamics, means when something is happening, how the complex growth modes we can see, then that will help to directly link process conditions to what we are seeing as a microstructure. This will also help to do some modeling or simulations and so on. So when there is some challenging system, like I was showing different microstructure, they all can be seen if they are difficult to model or if they want to difficult to make in the artificial way. So these are the importances of why in situ solidification is required. And now the challenge is when you want to capture that in the real time, liquid phase will um, undergo different things like contamination or oxidation, because we are heating to high temperature that can react. So many problems are there, but need to design the setup properly, and if we design, it will work better. So in when I'm doing at the postdoc, so this is one another furnace we have developed, which you can see. So this furnace is kept here, and there is a camera here, and there is some X-rays are sent. When X-rays are passing through the material, if there are two phases, one phase absorbs more X-rays, and other phase absorb less X-rays. So you can see the shadow of material. By seeing the shadow, you can see how solidification is happening. So again, two zone furnace is made, and we can able to see when we melt the material, and we are also taking the video. And now with the help of real cooling, you can see how the structure is really forming. So for example, this is in aluminum 3 nickel eutectic. Initially, it is fully liquid here. You can see when you are cooling, these solid phases, two solid phases are growing like this. This is when you are cooling it down. So this is actually captured by using a furnace. And when we send the X-rays in this, and here is the material, and this is a furnace where you can cool heat the sample. And when the X-rays are going to the detector, nickel absorbs more X-rays and looks like very black, because X-rays are not passed through nickel. And aluminum is very light element, and aluminum looks very bright. So based on this, this is aluminum and this is Al3Ni, and this is liquid. From the liquid, two solids will form and grow like this. This is captured for aluminum and nickel eutectic system, which means what eutectic I explained before. This is all done in Brookhaven National Lab synchrotron facility, where synchrotron means they actually circulate one electron and generate X-rays, and from that X-rays you can take the projections or you can take the shadows of your material and see when you are cooling how the really the material is growing. This is one example. The another example is uh, for this type of material, the aluminum zinc material, aluminum germanium material. How this is very complex material compared to the previous two rods are growing or three rods are growing. This how this type of structure is formed. To study that, this is the real time data, how the material is, this is the solid below, the top is liquid, and this is how it is forming. I put the same video into different images. You can see first germanium, this type of two tips are there, and that is growing up with the time. This is with 10 seconds, 20 second, and 25 second, 29 second, 34 second. And when it is there, the aluminum fingers type of things are spreading on this line, along this line, and that line is nothing but this line. And there is another line here, that is this line. You can correlate what I was referring to. And this structure evolve something like this. This is like a fish bone type of structure inside a material, but that structure of that material form as shown in this type of thing. So what it means is, if you have real time imaging, we can able to um, capture how really that is happening, and that will help us to understand how to change the internal structure, and then the material itself, and that leads to advanced material making. So similarly, not only that, by seeing this, we can hypothesize, or we can tell really how the microstructure is forming inside that. We can create something schematics, and also these are actually the crystal structures of that material. We can combine that, and we can also study them in the 3D. This material is actually converted into a 3D structure by doing something called a CT scan. If we do CT scan, we can generate the three-dimensional picture of what you are seeing. Through that technique, we can able to make a 3D structure. This is actually the 3D structure, and after that, with computers, we can remove what is germanium into one phase, one image, and what is aluminum into another image. Then we can also see how germanium is there inside this, and how aluminum is there inside with different features, and we can analyze them, and we can calculate the curvature, or we can calculate. Here I was showing one feature, but you can do different things, and we can get lot of information about the microstructure, and how the structure of material inside is there. Similar to that, you can also see using optical. So this is one other professor, Akamatsu. They put a camera with optical light only. So here they do the solidification. When they are doing the solidification, they first, if they do for aluminum nickel, you can see how it is evolving. For the case of aluminum silicon, this is silicon, this is aluminum. You can see how it is growing, and how it is branching, how it evolves with time, all you can see. This is also different structure inside the material. By understanding how you are cooling, how you are putting thermal gradient, this will influence the final resulting microstructure.